for joining us for this first CPM seminar of the year. This is a joint seminar between INFI and CPM. There will be some relevance to quantum information as well as material science. So it's my great pleasure to welcome Anthony Sigillito, who comes to us from the University of Pennsylvania. He's been there since 2021 as an assistant professor in the Department of Electrical and Systems Engineering. Previously, he was an associate research scholar at Princeton's Department of Electrical and Computer Engineering and in the Department of Physics as well, where he also held the Dickey Fellowship. He received his PhD in electrical engineering at Princeton in 2017. And I think I met you around the time when you were finishing your PhD at some conference in New Jersey. And I knew about your work before that. He's done some very interesting work in spin resonance and 2D electron systems, a lot of really cool stuff. He was also the recipient of the Google Research Scholar Award in 2022 and the Intel Rising Star Award in 2023. So it's my great pleasure to welcome Anthony.
A really kind introduction, Bill, and it's really a pleasure to be up here. It's certainly a little bit colder than Philadelphia, but I've worn layers, so we're good. As Bill said, it's my pleasure to tell you today about work that I've done really throughout my postdoc career as well as in my faculty career, and on really developing this platform for quantum information processing based on spins in silicon. And in particular, using lithographically defined quantum dots. So first, just to keep it pretty general, I think most of you have heard about quantum computing. Oops. Okay. You know, part of that is that, you know, it's in the news all the time. And, you know, there are constantly headlines. This slide is now a few years old. I actually tried to update it last night, but all the slides were about dropping stock prices for D-Wave following comments by NVIDIA, and they didn't seem quite as optimistic as these older headlines talking about you know, Google's involvement and Intel and Microsoft and all of these really industrial giants that are jumping into the quantum computing space. And it's really accelerated the progress of the field, in part because they're really interested in looking for applications, near-term applications for these quantum computers. And of course, they're also putting in major investments necessary. But, you know, even if they're making kind of a big splash, and we're hearing a lot about quantum computing, you may ask why we care. And if you would have asked any of us 10 years ago, 15 years ago, maybe, why we were interested in quantum computing, almost everybody would have said Shor's algorithm. If you can build a quantum computer, you can factor numbers really efficiently. Okay. In recent years, we've been hearing a lot about other applications. This can be everything from looking at protein folding, so finding ways to design new drugs and drug delivery mechanisms. Nitrogen fixation is one that we hear a lot about. You know, you can simulate this enzyme nitrogenase and find more efficient ways to engineer fertilizer and produce fertilizer. It accounts for something like 2% of greenhouse gas emissions globally. So, you know, if you could find better ways to produce ammonia for fertilizer, it would have a big impact, just not in, you know, in terms of being able to feed people at a much lower cost, but, you know, could also have environmental impacts as well. And of course, the list goes on and on and on. There are optimization problems that are well suited to this. Risk assessment, you know, the financial industry has a lot of interest in quantum computers. Traffic optimization, now machine learning applications are becoming kind of popular, and the list goes on and on and on. So our hope is that if we could build a universal quantum computer, that we could do some really interesting things that would really benefit society. And I'm not going to say much beyond that, except we need to now ask, how do we build a quantum computer, and what do we need if we want to have a universal quantum computer, something that could be useful? And luckily, David DiVincenzo, now almost 25 years ago, wrote down a list that is useful for us experimentalists. It's sort of a checklist of things that we need if we want to be able to build a universal gate-based quantum computer. And the first one, we can go through it really quickly, is that we need a scalable physical system with well-characterized qubits. So basically, there are two parts to that. We need to have some quantum mechanical two-level system. So we need a bit for the system, and it needs to be scalable. So it's not sufficient to just have, one really good bit. You need to have lots of bits to build up the system that becomes your quantum computer. We need the ability to initialize a qubit to a simple fiducial state. That's a fancy way of saying that you've got to be able to control the input of your quantum computer. You've got to be able to prepare the initial state. Otherwise, you have a garbage in, garbage out problem. We need long relevant decoherence times. So basically that says that if we store information in a bit of the computer, we better be able to store that information for time that's long relative to the time at which we need that information. So we've got to be able to store information for time that's long compared to the length of the algorithm. Okay, otherwise if we're losing the information, if bits are randomly scrambling throughout our calculation, it's going to be a problem. We need a universal set of quantum gates. So we need to be able to manipulate our bits, our quantum bits. And this means that we need both single qubit control as well as some interaction between the bits. So we call those 2 qubit gates. And then finally, we need a qubit specific measurement capability. So we need to be able to actually look at the output of the computer. Okay, otherwise, if we can't measure anything, then our computer's not going to be very useful. So just to give you a sense of where the field was, really when I sort of made my switch from donor-based systems to lithographically defined quantum dots, we checked a couple of the DiVincenzo criteria, but not very many. So I think that at least for silicon spin qubits, we had the ability to initialize the system into a known initial state, and we did have a measurement. What we did not have was really a scalable system. And in fact, we've made some progress over the years towards that end, really starting with work that came out of Jason Petta's lab from my colleague David Zajac, in which he found a way to scale these systems, at least in one dimension. So we went from like 1 qubit devices and 2 qubit devices up to like a 10 qubit device. And, Intel's made sort of 50 qubit scale devices these days using a similar sort of architecture. Now it scales in one dimension, but I've put it in yellow because we're not really there yet. These systems, eventually we're going to want millions of qubits. And if you can make one really long chain of qubits, that's great, but ideally we can scale in multiple dimensions. Second, we needed long relevant decoherence times. So Sego Tarucha's group was really the first ones to do this with silicon quantum dots back in 2018 now, where they found, and this has been known for a very, very long time, that the amount of time that we can store the information, the coherence time, is limited by the nuclear impurities in the silicon. So we have, so there's a nuclear spin, it's silicon 29. And qualitatively, you can think of it as having it has a small magnetic moment, and that means that your material is magnetically noisy. So those nuclei can flip and flop about. They cause magnetic noise, which then decoheres your system. Okay. Well, since I think it was 59, George Fayer, way back then, knew that coherence times and line widths were limited by nuclear impurities in silicon. And we knew that we just needed to grow the material, basically, in order to take advantage of silicon 28. So it turns out that silicon has one isotope, silicon 28, that is nuclear spin 0. I'm sorry, it has 2 isotopes, silicon 30 as well, but we enriched to silicon 28 to remove all those impurities. And finally, we needed a universal set of quantum gates. And this was kind of the hard one, and the one that I may have worked on the most in Jason Petta's group, where we demonstrated a C0 gate for electron spins. So this was back in 2018, where we showed for the first time in silicon, this is an entangling interaction. We knew before then how to control single spins, but we didn't really know how to do with any high fidelity multi-qubit operations. At the same time, Van der Sijpen's group at Delft demonstrated similar fidelities, and in fact, higher fidelities using a C-phase gate, which is another universal 2-qubit gate. So just to show you sort of the pace of progress in the field, I've sort of gone through it this way. If we were to look at sort of the state of the art way back in 2017, okay, I've put a few of the technologies. There are other technologies for qubits. Probably the leading one these days is superconducting qubits. Ions and atoms have also made a lot of progress. But back in 2017, the number of qubits that we demonstrated was only 2. The system, at least in silicon, with the graphically defined quantum dots. We had no 2-qubit gates. Our 1-qubit gate fidelities were 99%. We want those to be as close to 100 as we can. So compared to all other technologies, we weren't looking great, okay? But of course, we've made a lot of progress. So if we step to 2018, and in particular, you'll see where we were really lacking was, well, part number of qubits, but also gate fidelities. So we really needed that 2-qubit gate. So in 2018, we had a 75% C0 gate and 89% controlled Z. We had a long ways to go, but we were happy to just be on the board. In 2019, in particular configurations of the device, we could get to 98% controlled rotations and almost 90% controlled Z gates. And then as I just keep stepping through the years, you'll see that we've gotten to the point where the state of the art's almost 3 nines in terms of the 2-qubit gate fidelity. 1-qubit gate fidelities are beyond 4 nines these days in some of the best devices. And we're really happy with that. So we still have work to do in terms of scaling the systems, but at least we're comparable to other technologies. Right. So for the bulk of this talk, I'd really like to go through the physics of how these devices work. And I want to start by discussing the design of the device, how we trap the individual charges and use them for computation. I'll talk about single qubit operation, 2-qubit operations, and then finally I'll give you maybe a brief outlook, depending on time, of ongoing work within my own lab at the University of Pennsylvania. All right. So our qubit consists of a single electron, and we're going to encode the information in the magnetic moments of that electron and the spin of that electron. And the first thing we have to do is just trap the electron. Okay, we need to be able to isolate those single charges. And we're going to do that by first confining the electrons in a wafer in what we call a 2-dimensional electron gas. So we're going to have our collaborators at HRL grow us a nice wafer of silicon. We're going to grow on top of it silicon germanium. We're going to put a thin layer of 28 silicon, a little bit more silicon germanium, then we have sort of a protective silicon cap up top. And what this does is it takes the silicon germanium is not well lattice matched to the silicon, and it's going to strain the silicon pretty significantly. And if we were to look at the conduction band, it looks something sort of like this. Okay, we have a little kink. So this is the energy of the conduction band as a function of depth in the wafer. And we see that we end up with this well. It's called a quantum well, and it's where our electrons live. So the electrons are about 50 nanometers below the surface of our wafer. This is the surface. They're sandwiched between silicon germanium layers. And for the purposes of this talk, at least, you can think of the wafers as providing us with basically a 2-dimensional sheet of charge. Conductive sheet of charge, but 50 nanometers below the surface. Now that confines us in 1 dimension. We need to be able to confine laterally as well. And we're going to do that through nanofabrication. And in particular, we're going to use an architecture known as the overlapping gate architecture. So these are images taken back from when I was a postdoc in Jason Petta's lab. But the first layer, we're going to call the screening gate layer. So we have in light gray aluminum, dark gray silicon. And when I go to tune up a device, okay, so think about this. So the silicon has a sheet of charge below it, below the surface. If I make all of these aluminum gates negatively charged, it's going to push charges away. All right, it's gonna mean that electrons don't really want to live underneath these three aluminum gates. But you'll see that we actually do have little wires right here of dark gray where electrons can still live. Okay, so we're basically defining two little nanowires. We're going to put down a second layer of gates that's insulated from the first layer of gates. We call these plunger gates, and we have these little fingers that lay down right over those nanowires. I'm zoomed in now to this region. The scale bar here is 500 nanometers. So there's 100 nanometers between the center gates. And eventually I'm going to make these positively biased. And that means that electrons really want to live underneath these regions. But in fact, the second layer of gates lays on top of the first layer of gates. So the first layer is going to screen the second layer. So the electrons only see the positive potential here and here and here and here. Now we still have open regions of silicon, and we're going to close those off using a third layer of gates known as barrier gates. And these barrier gates we're going to make relatively negative, such that we can take a cut through this device. And at least in the cartoon world, it would create something that looks like a washboard potential, okay, below those gates. And electrons will sit in all the dimples. So here's basically the stack up of that 4-qubit device. We have basically an array of quantum dots up top. We have 2 charge sensors down below. The charge sensors are going to be used, as I'll show you in a minute, to determine the occupation of the array. And we can do a console simulation of the potentials and everything just to see that indeed we end up with 4 potential wells up here and then 2 additional quantum dots. So those charge sensors are important. Sorry, because they allow us to map out basically the electrostatic landscape of the device. And what we're going to do is an experiment here, where I just take 2 of those sites and 2 of the plunger gates. We're going to take the left plunger gate, the right plunger gate of 2 sites, and I'm going to vary their voltage. As I change that voltage, if I think about that quantum well, what I'm doing is as it becomes more and more positive, electrons want to live under that gate more and more and more. To the point where as I get to a certain potential, I can have, instead of 1 electron in the device, I could have 2 electrons in that potential well, or 3 electrons. So I start down here with the gates relatively negative. As I sweep them up higher and higher in voltage, at some point I'm going to see something change in the device. And those changes are when you get an additional electron to hop onto those sites. So if I'm labeling here in numbers, the occupation of the left dot versus the right dot. So 0, 0 means the device is empty. 1, 0 means there's 1 electron at the left dot, 0 in the right. 1, 1 is where we usually want to operate, where we have 1 electron in both sites. Now the color scale here is going to be, it's basically differentiated current through that charge sensor. Oops, keep forgetting this doesn't work. If we look at these charge sensors, these form effectively transistors. The device itself looks a lot like a transistor. And if I've got a current that flows through here, so going from source to drain through a quantum dot, it's going to depend strongly on the voltage of the gate. You know, any transistors, we apply a voltage to the gate as an IV curve that turns on. Same thing happens here, except that we have very close to this gate another charge. Okay, so as I add an electron to a site near our single electron transistor, or our charge sensor, it's going to change the electrostatic environment and it can change the current that flows. So effectively, that's what we monitor. And whenever we see a change in current, that means that we see a change in charge occupation. All right. I should say if there are any questions, feel free to interrupt. I love questions. So, but if there aren't, let's go on to single qubit operation. So we see how we trap individual charges. Now we want to manipulate them. And And the way that we're going to manipulate them is that we're going to make use of that, well, that magnetic moment. And if we think about an electron in a magnetic field, if it's got a small magnetic moment, we put on a field, it's going to experience a torque. It's going to want to precess. Okay. And this is just known as Larmor precession. And I can plot here this spherical coordinate system, basically a couple of arrows. All those arrows are vectors, you know, and they're just, we have an ensemble of spins here. I have them starting in various positions. I apply an external magnetic field along the blue arrow, and they're going to rotate. But we'll notice that there are two special arrows, straight up and straight down, the red arrow and black arrow. And those are not moving, right? They're known as eigenstates, stationary states. And in fact, they're going to form the two states that we're going to use as effectively the zeros and ones of our qubit. All right. Now, if I want to drive my spin from 0 to 1, or spin up to spin down, you may naively say, okay, well, if I apply a magnetic field, it experiences a torque. So I just apply a magnetic field maybe perpendicular to that external field, and the spin would flip. In fact, it doesn't quite do that. If I apply that external field, well, it's stationary. So we just sum these two vectors together, head to tail, and we see that we tilt the axis of precession, but we don't actually drive the red arrow down to the bottom, black arrow to the top. Instead, what we need to do is apply a field that rotates the spin, something that's dynamic. So if I apply now an external field that rotates at the same rate as the spin, you're going to see that it's going to take those arrows. The torques no longer average out. The spin up can go to down, and down can go to up. Okay. So conventionally, this is how people manipulate spins. You shine in a magnetic field that rotates with the spin. It's a microwave field, effectively. If you apply a linearly polarized field, it's going to have left and right circularly polarized components. One of them is going to rotate with the spin. The other one will average out. But it turns out that it can be a challenge to get really large microwave magnetic fields down to the bottom of our cryostats. And in particular, it's hard to localize those fields to the spin and not affect everything else in the system. So we're going to use something, sort of a variation of this that we're going to call electric dipole spin resonance. And what we do here is we take our device. It's now got a big sort of omega-shaped thing on top of it. And this is basically a cobalt layer. It's a few hundred nanometers thick. It's about a micron on a side. And it's a magnetic material such that if I apply a magnetic field from left to right in this picture, it's going to polarize these legs, okay? So we can think of this in sort of the cartoon picture as having a bar magnet on the left side and a bar magnet on the right side. I'm taking a cut right through that red line. My electron lives down below, about 50 nanometers below. And if I have a magnet right here and a magnet right here, there's going to be a field between the two. And it's going to fringe off to the side, right? We're going to have a field that goes that way. And I can actually take an orthogonal component of that field, and it's pointing down on this side of the device, and it's pointing up on this side of the device. That means now if I jostle the electron back and forth, well, from the electron's reference frame, it's seeing on this side of the well, a downwards field, on this side of the well, an upwards field, and it's going to see a time-varying magnetic field. So this means that by moving the electron, I can actually cause it to see a time-varying magnetic field, and I can drive it instead of using magnetic fields, using an electric field, because electrons respond very strongly to electric fields. Okay, so we're about halfway there in terms of understanding the device. We know how to trap charges. We know how to manipulate single spins. Now I want to show you how we can initialize and read out spins. And I'm going to sort of change our picture a little bit. Instead of just looking at this, what we call a charge stability map, we have 0 electrons down here, 1 electron on each side up here. So the zoom in of the earlier figure you saw. I'm going to consider two quantum wells that are my left dot, my right dot. They have an energy level for the first electron occupying the left dot and the right dot that's then Zeeman split. So it's split by the difference in energy between that spin up and that spin down electron within that well. And to start the experiment, so this voltage configuration corresponds to being down here. I'm just going to change my voltage a little bit to change the energy levels. And as I increase the voltage on the right side, it's going to lower the energy. I'm going to increase it to the point where I straddle the Fermi level of the device, such that a spin down electron can hop in, but a spin up electron will require a little additional energy. If it does hop in, it can fall right back out. A spin down electron will tunnel in, though, it'll get trapped. So then I can plunge down deep and then go to the 0,111 charge transition on the other side of the device and allow second spin down electron to tunnel in. And at this point, I've selectively initialized myself into the down state. So I know the initial state of my processor. We're then going to do some manipulation. I'm going to shine in an RF electric field, and we'll scramble the spins, and we want to read them out. Well, it turns out readout's basically the same as initialization, just in reverse. So I'm going to go back to those same points right here. And at the same time, I'm going to monitor the current through that charge sensor. Remember, there's that sensitive single electron transistor whose current depends on the electrostatic environment. And if I just wait some period of time, a couple milliseconds, at some point, I can see a change in that current. And if I see a change in that current, it means that an electron has moved out of the device. And then it implies that it must have been a spin up electron, because a spin down would have had enough energy. Now, of course, now you've got an empty dot and a spin down electron can tunnel back in. So those signals are finite. So it'll happen for something like 500 microseconds here. But however, by monitoring that signal, I can imply that I had a spin up electron. I can do the same thing on the right side. I see another little blip in the current trace, and I know that I've seen an electron. So by the way, this is real data. Our data has even gotten cleaner over the years, to the point where instead of having millisecond timescales, we can have similar data in sort of microsecond timescales. But it just gives you a sense of what signal to noise of the single charge hops look like. All right, so we have readout, we have initialization, we have single qubit control, but let's look at some actual device. And one of the first things that we have to do is actually figure out what our qubit frequencies are. Okay, so we're going to do a spectroscopy experiment where effectively what I do is I shine in microwaves. I'm going to vary the frequency of the microwaves along the x-axis, and I'm going to read out all 4 electrons, or all 4 quantum dots simultaneously, or I'm sorry, serially. And I'm going to find that qubit 1 has a little peak at around 16 gigahertz. Qubit 2 has a peak at like 16.7, and qubits 3 and 4 are a little closer together, at around 17.7, 17.9 gigahertz. And you may ask, why are they all different frequencies? And it's by design. So if we look at this device right here, this micromagnet, it's not really symmetric, right? We have this little ear sitting off to the side. We have a sort of slanting foot right here. And this ear in particular acts sort of as a magnetic choke. So if I have a magnetic flux line coming up, they're going to want to get pulled right into this region. And that means that electrons on the left side of the array are going to have lower external magnetic fields than electrons on the right side of the array. We like this because it means that now we have addressability. So qubits all require different frequencies to do manipulation. If we look back at that old data, if I affect qubit 2, I'm not exciting qubits 1 or 3 or 4. Okay, so I can frequency multiplex and control. All right, so once we find a qubit, we want to know how good it is. Remember, we need to have coherence times that are long compared to the amount of time it takes us to do an algorithm. So there are two metrics that I'm going to look at here that are often quoted. These are known as T2 star and T2. So for those of you who are experts in the field, T2 star is basically how long I can store information if I do nothing to it, if I just let it idle. T2 is how long I can store information if I play a little trick that filters out some of the low frequency ones. All right, so looking at the 4 qubits, I see that qubits 1 and 2 have coherence time, T2 stars that are between 1.5 and 3 microseconds. Qubits 3 and 4 have T2 stars that are around 10 microseconds. We believe that the difference there is actually due to the micromagnet. These two sit in a gentler gradient, these two. But we're happy with that. If we go back to the early days, you know, pre-silicon, when people were doing things in gallium arsenide, T2 stars could be as short as, you know, a few nanoseconds to tens of nanoseconds. They got quite a bit longer as people learned how to control the nuclear environment through a variety of techniques. But natural silicon then was around half a microsecond. And here we're seeing about another order of magnitude improvement in the ideal dots. Yes?
Can you explain the oscillation frequency in the T2 star measurement? I thought that should be 16.
Well, yeah, great question. So what we're doing in the T2 star measurement is you prepare a coherent state. So you start out with the qubit in the 0 state, you tilt it down using your RF pulse. And you're right, it's gonna oscillate at like 16 gigahertz. But you're gonna measure now, you're gonna lock into that frequency, and then you're gonna project it back up to, say, the 0 state or the 1 state. And what's happening here is if we lock to that frequency, you'll see a simple decay just like this. But let's say that we're off by like a kilohertz or something, then you'd see an artificially short decay because you're going to accumulate some phase. So what we like to do is we detune by like a megahertz or 2 megahertz. And then that way we get lots of oscillations, and then we can fit to the envelope, and then we don't worry about being perfectly locked. So it's sort of an experimental technique, but typically that's how we show the data. Good question though. Any other questions before I move on? Yeah, so I've now told you about the coherence and line width, well, the coherence times of our qubits. I haven't really told you how quickly we can manipulate things. Usually 1 qubit gates are ordered tens of nanoseconds. 2 qubits are maybe a little bit longer. But ultimately, we want to know how many operations we can do within a given period of time. And the best way to benchmark these systems is through something known as, at least the way that we like to start, is through Clifford randomized benchmarking. So this is a technique where basically what I'm going to do is take some long string of quantum operations, quantum gates. I'm going to randomize them. I'm going to draw these gates out of some list of gates known as the Clifford group. And as I apply these gates to my qubit, I'm going to keep track of what I've been doing. So I know ideally what my qubit state should be, such that at the end I can return myself using some non-random gate to a known state. Okay, maybe it's my initial state, or maybe it's an inverted initial state or something. And if I do this many, many times, varying the composition of the gates as well as the length of these strings of gates that I'm applying, it's going to tell me something about the fidelity of being able to do a quantum circuit. Okay. It turns out that we can get a little bit fancier, and instead of using a random sequence, I can use a quasi-random sequence where every other gate, the blue gates are not random. And if I compare the decay of the fully random sequence to the one that's weighted more heavily towards these non-random gates, it tells me something about the contribution to the infidelity of my sequence due to these non-random gates. Okay. So I can take a whole family of measurements. Here's some example data where I'm going out to something like 2,000 operations on my single qubit dots. And this is, of course, on a log scale. I'm looking at the decay here. And if I fit to the decays for just a purely random sequence versus a sequence that then has a whole bunch of pi/2z rotations or pi x rotations sort of sprinkled in, I can back out a whole table of fidelities for these gates. And we see that, again, this data is now a few years old, but we had beyond 3 nines across the board. In fact, in a lot of cases, beyond 4 nines for these operations. And this is pretty typical these days. So we're happy with that performance. I mean, single qubit gates are working really pretty well. Now, 2 qubit gates are a little bit more complicated. And for electron spins, generally, 2 qubit gates are mediated through something known as the exchange interaction. And unless you've taken a quantum mechanics class, you may not know what exchange is. But I find that a lot of people have heard of at least the Pauli exclusion principle, which arises due to exchange. And basically, it says that 2 fermions can't occupy the same quantum state. So if I take my 2 electrons and I push them together such that those 2 quantum dots are sort of pushed together onto almost 1 quantum dot, there's going to be an energy penalty for having 2 electrons in the same state versus 2 electrons in opposite spin states. Okay. I've put down sort of a simplified Hamiltonian here. As you can probably already tell, I don't go into much math in this talk, but I do want you to notice that if we look at the Hamiltonian, there are only a few terms. There's a Zeeman splitting term, so let's do the external magnetic field. We have the J term, which is exchange, and then we have delta EZ, which is the difference in Zeeman splitting between site 1 and site 2 dotted red. Now, we have some experimental knobs that we can tweak. One of them is we can change the magnitude of J. We can also change the magnitude of delta EZ as well as EZ. Delta EZ is done in lithography. We make the device. But if we look at the case where we have delta EZ very large, this Hamiltonian almost looks diagonal, right? But if J is large, it's not. So that means that by playing with the relative magnitudes of those terms, we can actually find different regimes in which we can do different, in which we see different dynamics for a 2 qubit system. Okay, so the knob that we can change dynamically is always exchange. And if exchange is small compared to that external field, there are some primitive gates that we can realize. So there would be things like controlled Z's. We can do this resonant C0 gate that we had demonstrated. You can do a resonant swap gate. And the opposite regime, where delta EZ is much smaller than J, so the exchange dominates the interaction, we see something that looks more like a swap operation, like square root of swap. Yeah.
Is J related to the distance between the 2 electrons?
Sorry, say that again.
Is J related to how close the electrons are?
Yes. So it's basically equal to the overlap in the wave function. So as we push the electrons closer and closer together, J goes up roughly exponentially.
It's like an overlap at the all.
Exactly. Yep. Other questions? Okay, so I don't have time to go through everything, but I will at least explain this resonant C0 gate, maybe mention that C phase type gate. And I like it because the resonant C0 is kind of easy to understand. So if we go now to, this is a slightly different device. This is a 2 qubit device. Same physics as that 4 qubit I walked through. We have a charge sensor down here. In the absence of any field gradient and any exchange interaction, we can draw the energy level diagram right here. It's really simple. So up is going to be the highest energy state, down is the lowest energy state. And if we're in the left-right, I'm sorry, the down-up versus up-down configuration, those two have the same energy. Now, of course, we have a field gradient, and that means that the left spin and the right spin see a different Zeeman splitting, and that means that the left versus right spin being in up versus down now matters. Okay, so it lifts that splitting. Yeah, the green arrows I'm showing you basically the frequency of the left spin transition. Depending, and that's the right spin transition is shown in the subscript. And something interesting happens now when I turn on exchange. So if I push the electrons together, such that their wave functions overlap, remember there's an energy penalty for electrons in the same state versus opposite spin states. So that means the the down up versus the up down states are going to drop in energy compared to the down down and up states. And that's what we see. And now if I keep track of what my transition energies are, we're going to see that the left spin has a high energy transition to do the spin flip if the right spin is in the up state versus if the right spin is in the down state. Okay, so the frequency of this transition is conditioned on the state of the right spin. Now, this is looking at again, this 4-qubit device. I can do a really simple experiment, all right, where I prepare qubit 4 in the up state, and qubit 3, I prepare in the down state, but then I apply a microwave burst where I vary the frequency as well as the time of that burst. And remember, if I'm on resonance and I'm applying that microwave field, I'm going to see that spin flip and flop like we saw in the animation earlier. It's going to go from spin down to spin up, to spin down to spin up. So when I'm on resonance here at 16.617-ish gigahertz, I'm going to drive what we call Rabi oscillations. Now, simultaneously, what I'm doing is I'm applying a pulse to that gate that separates the two spins, that barrier. So I'm pulling the electrons closer together, turning on exchange. So that now if I repeat the experiment with qubit 4 in the down state, I see that whole pattern shifts. So I'm now driving oscillations when I'm at 16.61 gigahertz or something like that. Now this is great because now I can choose some frequency. We're going to call it FC0. It cuts through one of these two patterns. And a time TC0, this is just a 1D cut of those plots, where I can flip, for example, qubit 3 conditioned on the state of qubit 4. So if I flip qubit 3, qubit 4 is up versus not flip when it's down, that's a conditional rotation. And it's a conditional in particular, it's a conditional NOT gate. Now, there's something that's really swept under the rug here, and I just want to mention it really quickly, which is that when I turn on that exchange, when I pull those electrons together, there's a difference in the transition frequency for the left spin conditioned on the right spin. And that frequency is set by the rate at which that spin is processing, right? So in the top case, if the right spin is in the up state, it's processing pretty fast. If the right spin's in the down state, it's processing a little bit slower. So if I turn on that exchange, if I pull the electrons together for a finite period of time, well, and in one case, it's going to rotate fast, in the other case, it's going to rotate slow. I'm going to accumulate a phase, okay? So this is a conditional phase gate. And it's, well, it tends to be a little bit higher fidelity because the C0 gate requires us to calibrate out that C phase. So I'm just going to jump now to the kind of the state of the art for 2-qubit gates. So this is results that came out of Jason Petta's lab again, that sort of a holdover from stuff that I worked on many years ago. And what we've done here is we've taken these gates, these controlled Z gates, a C0 gate. This is a slightly different implementation of the C0. It's a detail. And we've done this Clifford randomized benchmarking again. But here, instead of doing it on 1 qubit, I'm doing it on 2 qubits. And instead of interleaving just random single qubit gates, I'm going to interleave 2 qubit gates. And when I interleave 2 qubit gates, I can compare basically my reference to the interleaved with a controlled Z versus the interleaved with controlled not, and I can back out the fidelity of those operations. Our single qubit operations are really high fidelity, so most of the decay that you see is coming from those 2 qubit gates, which are 99.8% for the controlled Z and 98.6% for the controlled not. So we're really happy with that. We've gone from, our first demonstration that had us ecstatic was a 75% C0 gate. Over the years, we've gone first 90 to 98, and we're up to 99.8% 2 qubit gates, which is good enough for where we are now. Any questions so far? All right. I've got like 9 minutes. Is that right?
Yeah, maybe it's good to end
I'll
in 5 questions.
Okay, I'll end pretty quickly. But I do want to just give you a quick outlook, which is that, if we go back to the DiVincenzo criteria, hopefully I've shown you that we've satisfied pretty much all of them. The one real challenge that remains, I think, is scaling these systems. Okay, so on small processors, we can get really high fidelity operations, but eventually we're going to want millions of qubits, if not hundreds of millions of qubits in long-term devices. And it's hard to do for 2 reasons, well, a lot of reasons, but 2 that I'm going to focus on are that these gates, in order to get those high fidelity operations, we're constantly recalibrating, feeding back on what's going on in the device. Okay, so there's a lot of calibration overhead associated with getting a high fidelity gate, and that means that there's a lot of downtime for the processor. And in fact, this doesn't scale well. As we get larger and larger systems, the calibrations become more and more expensive. We've got to find better ways to deal with that. The other is that measurements are going to be a real challenge, especially as we start to think about these really large arrays. Those measurements I showed were kind of slow, right? So they were millisecond in this initial data. There are better ways to do measurements, but we're not quite there yet. Yeah.
All right, so say you solve the green ones, you use more or less coaxial cables than like the usual kind of qubit or something per qubit. Like this is getting all of the information in and out. It's like a real challenge.
It is a real challenge, and it's well, I guess the question is going to be how we deal with that, how we start to scale these things. And one of the key questions that we're trying to answer in my lab at Penn, and I'll show you in a minute, some of the things that we're moving towards, is finding ways that we don't really need a lot more wires to scale a lot of qubits, or we don't need a lot more microwave sources, for example. If we just brute force it, if we keep going the way that we're going right now, then I think that you're going to have roughly 1 microwave source, 1 coaxial cable for every qubit, maybe every 10 qubits or something. So it's going to be similar to Google or IBM. The difference is that in addition to RF control, microwave control, coax cables, we have a lot of really low noise DC lines that have to go down. So each experiment has something like on a quad dot device, maybe 30 or 35 really low noise voltage sources that are biasing all of those gates. So people are thinking about ways to share voltage control over all those gates, such that you can find architectures where that scales reasonably well. And there are hopefully better ways to do the control that doesn't require 1 line per pair of qubits. That's something that we're definitely thinking about. If we can find better ways to control, then maybe there will be an advantage, but it's tough to say. I would say that, in the past, the bottleneck has been fab, and that's not so much the case anymore. I always like to show this picture This is one of the last devices that I made based in the lab. It wasn't hooked up to anything, and it's not something that we ever tried to measure. We'd never be able to measure something like this. I think it was even done on natural silicon because we never intended to measure. But we can show that we can make really large arrays. So this is like a 256 qubit array. In fact, it was fairly straightforward to fabricate. Controlling it would be hard because if I want to now do qubit gate between qubit 1 and qubit 256, I've got to do lots of swap operations. And if our primitive gate is a C naught or a C phase, we're looking at something like 3 of those gates per swap, which is a lot of multi-qubit gates to move the information around. So what we're looking for is a more distributed approach. And we want to make use of one of the, I guess, fundamental properties of the electron, which is that it's mobile, right? So if we have charges in our semiconductors, we can imagine moving them around. And in fact, because the information is stored on the spin of the electron, there's no reason that you can't move the electron and preserve that information, that quantum information. So there's been a lot of really beautiful work over the last few years. This probably needs to be updated. There have been a few key results in the last year in which people have been able to move using these interdigitated gates, electrons, coherently, one device to another device with very high fidelity. Now, these devices, they're beautiful. The results are beautiful. One of the challenges is that it's a little bit slow and it's a little bit complicated in terms of doing all of this fabrication. So one of the key thrusts in my lab currently is to develop a new architecture based on what we're calling resistive shuttles. So the idea is if I have a double quantum dot on one side and a double quantum dot on another side of the chip, and if I put a nanowire up on the surface, it's resistive. So we use an alloy of silicon and niobium to get high resistance at low temperature. If I look at this is what the gauge would be biased like. I can apply basically a voltage source differentially across that resistive shuttle. I could potentially, positively bias that channel to induce a nanowire that connects one double quantum dot to another. Now that alone doesn't buy me an interconnect. I need to be able to control the slope of this potential, and the way that I would do that, I take an electron into the channel. If I now apply a current through that wire, apply a voltage difference across that wire, I can basically create this slide that will electron from one side to the other. So we have these devices in the lab. We've been measuring them for close to a year now, where we have a double quantum dot separated by about 13 microns to another double quantum dot. We can load electrons, we can pull electrons out of the channels, and we're sort of working our way towards a full demonstration of coherent transfer of information. Maybe I'll jump through this in the interest of time, but I'm basically showing that we have spin control, we have charge control, and things are looking reasonable. And I'm just going to really quickly mention, because I know I'm out of time, that the other sort of approach that we're taking is an optical control of quantum dots. So instead of having wires everywhere, we now have a fridge set up in one of my colleagues' labs where we are generating terahertz control fields down at cryogenic temperatures where we can promote S-like orbital electron to a P-like orbital. This opens up a whole host of possibilities for multi-qubit gates that may be a little bit longer range, a lot faster. It also opens up interesting prospects for readout. I can show you the setup. This exists and is characterized, and with that, hopefully I've convinced you that we have a pretty interesting platform for doing quantum information processing. I think a lot of the work that needs to be done is going to be in sort of rethinking some of these architectures so that they are more scalable. And of course, I've got to thank all of the collaborators over the years, and I will take any questions. Thank you.